Hello and welcome to the EVM programming course. In today's episode, we will gonna look into data locations in EVM. So there are multiple places where data is being persisted in EVM, be it for the duration of transaction or, well, forever. Those are stack, memory, storage, Calldata, code. They all have their well-defined place in transaction execution flow, and we will describe them one after another. But please note that there are many aspects of all of those data locations that are not defined by the EVM. One example of it is ABI encoding and function selectors, which is defined for Solidity. Hence, I won't describe those topics here, but later when I go through Yul. Okay? First of all, let's go through the stack. This is primary data structure used for storing and managing operands during smart contract execution. As you know from the first episode, EVM operates as a stack machine, which is the primary data structure used for storing and managing data during computation. Stack can hold up to 1024 words. And keep in mind that word is 32 bytes in EVM. And all opcodes, apart from invalid, stop, and jump dest, are either taking something from stack or putting something to stack. And opcodes used to modify the stack are pop, push 1 to push 16, dup 1 to dup 16, and swap 1 to swap 16. So each of push, dup, and swap has 16 opcodes defined. And here are some key points about stack in EVM virtual machine. This is LIFO structure, which means last in, first out. That means that the last item pushed onto the stack is the first one to be popped from it. Stack is used for operand storage, so it stores operands for arithmetic and logical operations, as well as intermediate values during the execution of smart contracts bytecode. Performing each operation on the stack incurs some gas cost. And finally, it's scoped to the call context. That means that each time that external call is made, new empty stack is created. When the external call finishes, calling contract stack is restored. Okay, so now let's go to the example of how stack works. Okay, so you can think about storage as a stack of the boxes, where each box has 32 compartments for each byte. And as I said before, you have up to 1024 different elements that you can put there. So when your smart contract execution starts, you are having an empty stack. And then with each operation, for example, we want our first operation to push 2 bytes, byte AA and EE. And please forgive me that it slightly overflows the square. And then we are pushing 1 byte 87. So what happens now is that this operation puts on the top of the stack, and the operation that was there before is pushed down the stack. So this is what I meant by saying last in and first out. Next, let's say that I want to swap the elements. So after swapping all these elements, we will end up with the AAEE bytes on the top and 87 at the bottom. But now you may ask, what happens if I have only 2 elements on the stack? And for example, I want to do swap 2. So I want to swap the top of the stack with this element. So I wrote it as empty, but imagine that it not exists, that I have only 2 elements on the stack. So imagine that it's this case. I have 2 elements and I want to swap this element with a non-existing stack element. What would happen is the transaction will be reverted with stack underflow. That means that you are trying to access the element that does not exist on the stack. And the last operation that directly modifies the stack is dup, which is duplicates the specific stack value. So we can duplicate any value on top of the stack up to 16. And for example, let's say that we want to duplicate this value, the value that is second on the stack. So after executing this operation, what we will end up with is again we duplicated the value that was on the second stack position, and we put it on the top of the stack. Now we have only up to 16 duplicates, 16 swaps, and 16 swaps. But this value is really small. But what if we want to have more than that? If we write some huge smart contract and we know that the value will not fit in? Well, until one of the most recent Solidity version, this would just not compile. You would receive error saying stack too deep. That means that you have too much elements on the stack to be able to effectively swap them and duplicate them. In the most recent versions of Solidity, it was fixed by moving overflowing values to the memory. And the last note here is how does it works in the context of EVM. Let's put that here and do one exemplary operation. Add. So opcode add takes two elements from the stack and returns back the sum. So if we have like here 3 elements, if the next opcode is add, it will take this stack element and this stack element, it will add them, and it will return back the result to the stack. So in this case, it will add those two numbers and the result will be AB75. It will take one element from the stack, and now the next element will go up the stack. Let's verify if what I saw was correct inside of the EVM playground. First, we are pushing 2 bytes AAEE, and of course, the first element is on the stack. Next, we are pushing 1 byte 87. We are swapping first and the second stack element. Then we are duplicating what was on the second place in the stack, and we are adding that. Okay, so this is exactly what I had here. And this is more or less how the stack works. Now, let's move to memory. So memory is a primary data structure used for storing and managing data during smart contract execution. It's used for return data from external calls, reverts, contracts creation, logging or emitting an events, hashing, setting call data for low-level calls, setting call return data, holding values that will overflow the stack, as I said before when I was talking about the stack. So it does quite a lot of things. You can think about memory as a RAM in your computer. So this is basically a temporary and expandable data area that smart contract can use during an execution. It is distinct from the stack, which is limited size and used only for more intermediate and short-term storage. And before continuing, please note that I will skip some parts of the memory description, as some of them concern the way that Solidity uses it, which will be discussed later in the Yul part of this course. Okay, and unlike the stack, which is, well, as a stack, stacked one after another, the memory uses linear data allocations. That means that it is like continuous byte array. And very important stuff, this you will see that everywhere in Solidity, but I will first mention it here. Every memory byte has a value of 0 until it is changed. So there is no concept of null values. And there are 4 related opcodes to the memory. It's mload, mstore, mstore8, and msize. The difference between mstore and mstore8 is with mstore you are storing whole word, which is 32 bytes, and with mstore8 you are storing only 1 byte, which is 8 bits. That's why it's 8 at the end. And again, the same as with stack. If you are doing any external call, you are receiving new memory array as well as new stack. Okay, and that is the difference between stack and memory. As I said, stack was expanded downwards, and memory expands as a normal array. So if you want to store anything there, you are just saying at which offset you want to say. So for example, if you want to store bytes 51, 41, 31 in the first word of the memory, you have to first push it to stack, then push the offset, and then call mstore. So you can see it here in EVM codes that mstore takes offset and value from the stack, and then it puts it into the memory. So after this is executed, it is stored here in these bytes. If you want, for example, to change only one byte, as here, you are pushing the byte that you want to change. Or again, you are sending the offset that you want to store it, and then call mstore8. And what is important here, what will happen after execution of this, the byte that will be overridden will not be this one, but this one. And you may ask yourself, why is that? In case of mstore, you are storing whole word. So you are storing whole 32 bytes. And what the value that you stored here is 51, 41, 31. But this is just a shortened version of 32 bytes filled up with zeros. So we have 0, 0, 0, 0, 51. And as I said before, like this empty means 0, and I actually skipped it for brevity, but you can take it for granted as here those are zeros. And when we run it in the playground, we can see the same. So first we are storing the byte that we want to store, and the offset that of the memory that we want to put it, and then mstore takes these stack values and puts it, and you can see that it actually stored it here. Next we are storing byte AA, the offset again, and after this operation we should end up with putting AA to the memory offset 0. Memory offset 0 is here, memory offset 1 is here, and memory offset 31 is here. So let me go, yes, just as expected, it puts it here. But what if we want to store some longer values, some more values? In case of memory, it will just grow. So the array, as you can see on this arrow, it will just expand rightwards to whatever value that you want. Now you might think, but if I try to add too much memory, the EVM operating node will not be able to store all this memory and it will crash. So I probably can perform an attack in which I'm allocating some huge memory in order for the operator to crash. So EVM has protection against that, and the protection is the quadratic memory expansion cost. So you can see in this calculation that we are calculating how much words we have. Remember what is 32 bytes. So in our case here, that we have like our memory consists of 64 bytes, which means that we have 2 words. The memory cost you pay for each new word that you add to the memory is this. So let's go through some examples and see how much will we pay for the additional memory. So let's define our memory size word. So storing 10 words costs us 30 gas, which is not much. When we increase that to 100, it's more or less 10 times more expensive, but you can see that it starts to grow a bit faster. And now what if we want to store 1,000 words? It is significantly more than only 10 times, but it's still bearable. Now what about 10,000 words? Okay, you can see that it's really now starts to take off and cost really big numbers. Remember that the block gas in Ethereum, for example, is 15 million. So, and this is right now what you pay with 10,000 words memory. What about 100,000? You can see here that it costs 19 million gas. So in case of Ethereum, which has 15 million block gas limit, you will not be able to allocate this amount of words. So if, for example, we were trying to mstore to this location in hexadecimal, or if we were about to use decimal notation, if you want to store it, it will revert with out of gas error for us. So where the memory is actually useful and where it has edge over stack. First, the most important thing is that, as you can see here, you may have really long memory with multiple bytes, and you can have like hundreds of elements in a memory, and you can each time just call mload and load like specific word that you want whenever it is. In case of stack, you can have only like the top 16 elements that you actually can access, and later you have like problems. You cannot do that. That's why you have to use memory. Another thing is each stack element is one word only. So if you want to store some long string or some long stream of bytes, you are not able to do that with stack. So for example, if you want to return multiple values from a function, then you have to use memory. If you want to use some long string, for example, in a revert message, you have to use it. If you want to read the return data from external function, you also have to use memory because it can span over multiple words. And last thing, memory together with stack is temporary. So after the call context is finished, for example, you have external call and the call ends, the memory and stack is cleared. The same goes with transaction. If the transaction ends, the stack and memory are being cleared. So with having that level of understanding of memory, let's go next to the storage. So storage is persistent and permanent data storage area associated with a smart contract. It's used for storing data that needs to be preserved between function calls and transactions. It provides a way for smart contracts to maintain state across multiple invocations. Apart from that, some key points about storage is that this is key value storage. So each value is single word, which is 32 bytes. And it's addressable by its key, which is also bytes 32. Again, reading and writing to the storage incurs cost, the same as memory and stack. However, in case of storage, it's way more expensive, and we'll dig deep into it when we'll talk about gas. Next up, every storage slot has value of 0 until it's changed, the same as it goes with memory. And related opcodes are store and sload. And now let's imagine how the storage works. So distinctly from stack and memory, you can read any value that you like. So in case of memory, we only were able to load less than 100,000 element. But in case of storage, this is a key value map. So that means that we can refer to any key that we want, from 0, 1, 2, up to the maximum value for a word, which is 2 to the power of 256. And you can store whatever value that you want there. So let's see some example. What I prepared here, that we are pushing to the last storage slot, which is the maximum value of bytes 32, and then we are checking if it was stored by reading from the same storage. Okay, the code is loaded. Okay, I'm pushing it to stack, and now store. If anything changed, yes, you can see that in the last store we have value 11. Now I'm pushing the same value and I'm calling sload. Sload will return me to the stack what is under specific storage value. And as you can see, 11 appeared here. So it works as it's supposed to. Let's see the last example. What happens if you try to load some value that you know that it doesn't exist? Okay, first, same as usual, just making sure that it works. Okay, so we have 11th under this slot, and now we are pushing 1 byte with value 1, and because we did not push anything, there is nothing there. What happens if we try to load it? Well, like nothing, it returns 0. So as I said, every storage value is initialized with 0 in EVM, so you can safely use it. Cool. Having said that, let's go into Calldata. So the name Calldata is a bit unfortunate and usually makes people confused. But what it really is, it's the input data that is supplied when a smart contract is called, be it via externally owned account or by other smart contracts. Because this is data that you are calling with, that means that it's read-only and you cannot modify it. And it's up to the smart contract to decide what you do with it. Of course, in case of Solidity, you are having API that tells you in what format the Calldata is expected. However, EVM itself does not impose anything to you. This is just the part of the agreement that you have. And usually you want to use it as much as possible just because it's really cheap. And as a last part, the related opcodes here are Calldata load, Calldata size, and Calldata copy. So again, let's say that this is our smart contract and it expects the message to be in particular format. So again, in case of Solidity, ABI defines how it should look like. So ABI defines that first 4 bytes are function selector, which is just the hash of the function signature, and then comes the actual data that you want to put. However, in case of EVM, you can program it however you want. So let's say that we are writing low-level contract and we expect that our first 4 bytes, just like in Solidity, mean what functionality to call. And then we take like 8 bytes of value 8 and value B. And we have here exemplary values. So this is what we expect. So Calldata is like similar to the memory in a way that it's also a continuous array. So how you would put it here in order to be processed properly by the smart contract, you would call it like that. Let's say that in our case, this is additional operation, then comes the first parameter, and then goes the second. So our user just comes, sends this particular transaction with the smart contract, and then smart contract can use Calldata load and Calldata size and Calldata anything to read this. Okay, so let's start with this simple example. First, we are pushing 0 element, and then we are using Calldata load to load our Calldata at offset 0 to the stack. And when you run it, okay, we have 0 pushed, and then we are calling Calldata load. And as you can see, the exact Calldata that we used here are pushed to the stack. And you probably already see this, but it's important thing. If the Calldata load is less than a single word, which in this case it is right padded with zeros. Okay, cool. So we have everything concerning Calldata. And now finally, let's go to the code. So code, this is the bytecode that represents the executable instructions of a smart contract. When you deploy a smart contract on Ethereum blockchain, what gets stored in the blockchain is the compiled bytecode, which is just a series of EVM instructions. Additionally, what you have to know about the code is that the max contract size is 24 kilobytes. It's immutable. That means that you cannot change it. And opcodes related to the code are code size, code copy, external code size, external code copy, external code hash. You may ask why only we can have like 24 kilobytes smart contracts. It seems really small compared to the normal programs that we run. You have to know that each time that you are interacting with some contract, it has to be read from the storage, which is, as we know, costly operation, and it has to be stored in the node RAM during the execution. So imagine situation when you have like 2 megabyte smart contracts and you are loading like hundreds of them. That means that EVM node could not be able to hold it everything in RAM and it would crash. So again, this is just a security measure of EVM. This is a quick example. We have some exemplary operations here. And as you can see here, I was using mnemonic, which are the human readable version of the actual code. However, what EVM actually operates on is just the operation. So 60 is just push one and now the number. So if you would translate that, you would end up with this mnemonic that are easier to read for us, but the node actually uses this as a code. So this is what it's stored on chain. So that's all that you need to know for now about the code. We will definitely go back to this topic when we will talk about Yul. There will be more useful and you will be able to grasp this topic a bit more. But for now, that's all. We went through all the data locations which are there in EVM, and in the next episode, we'll go through opcodes. So I hope you liked it and see you in the next one.